Testing, can you hear me? Hello. I don't have this video on public right now. It's unlisted. But can you hear me though? Okay, this video is public now. So can everyone hear me? The book, I'm going to be reading a new book today. It's called Discrete Mathematics and Open Introduction. I'll just switch to full screen. Uh, so currently I'm reading two books, this one and the calculus one. And yeah, so I will just start reading this. What's all this? Tree text, math text. Should I read the front matter? What's this? Hmm. What is colophone? Also, I had a cold, so that's why my voice sounds like the way it does. Also, this work is licensed under Creative Commons, so you guys can share it and make notes about it, whatever. Okay, let's just go to the first chapter. Well, technically, it's chapter 0. Defining discrete mathematics is hard because defining mathematics is hard. What is mathematics? The study of numbers. In part, yes, but you can also study functions and lines and triangles and whatever. Or perhaps you want to say that mathematics is a collection of tools that allow you to solve problems. So what sort of problems? Well, those that involves numbers, functions, lines, triangles, whatever your concept of of what mathematics is. Discrete math could still ask about a range of function, but the set would not be an interval. Consider the function that gives the number of children of each person reading this. What is this range? What is the range? I'm guessing it is something like 0, 1, 2, 3, 4. Maybe 5 or 6 is in there too. But certainly nobody reading this would have 1.32419 children. The output is discrete. This output set is discrete because the elements are separate. The inputs to the function also form a discrete set because each input is an individual person. There are many discrete mathematical objects besides set of numbers. We will introduce some of these in section 0.2. Studying these discrete structures is the main focus of discrete mathematics in this book. However, the reason we want to study these structures because they provide a way to model real world problems. Throughout this book, you will see investigate activities like this one. Answer the questions and these as best as you can yourself to give yourself a feel for what is coming next. So, this one over here, where does it? Oh, even larger numbers for old lady. Okay. Uh, the most popular mathematician in the world is throwing a party for all of his friends. To kick things off, they decide that everyone should shake hands. Assuming all 10 people at the party each shake hands with every other person, but not themselves, obviously, exactly once. How many handshakes takes place? How do we, like, do they answer these questions? Everyone, sorry, uh, all 10 people at the party each shake hands with every other person, but not themselves, obviously. So there would be 10 people. One person shakes hands with nine of them. The other person shakes hands with also nine of them, right? Hold on. Let's make it simple. One, two, three, four, five. Let's do five instead. So this person one, two, three, four. And then for this person one, two, three, but we already counted this. For this person one, two, but we already counted these two. So four times three times two times one. I should also open Lesmos just for the calculations and stuff. So I'm not good at mental math. Lesmos. It's 4 factorial, right? Can't remember what that is. 5 times 3 is 12, 12 times 2 is 24. Yeah, that's what it is. So for 10 people, it would be 9 factorial, right? Hold on, no, this is not correct. Why did I do factorial? Should be plus 4 plus 3 plus 2 plus 1, 10. And then 9 plus 8 plus 7 plus 6 plus 5, 35. And then plus 10 from here, so 45. 45 handshakes. At the warm up event for Oscar's All Star Hot Dog Eating Contest, Al ate one hot dog. Bob then showed him by eating three hot dogs. Not to be outdone, Carl ate five. This continued with each contestant eating two more hot dogs than the previous contestant. How many hot dogs did Zeno, the 26th and final contestant, eat? How many hot dogs were eaten in total? So we have one, and then three, and then five. Oh, this is just one, eight, two, three, four, five. We have one, three, five, one, three, five, seven, nine. So it's plus two, right? Plus two, plus two. So the sum of an arithmetic series. So this is like the first term. and the first term plus the difference, and then the first term plus the difference twice, all the way till first term times n minus 1 d. N is like the total number. So here it's 1. So n is this 1, 2, 3, 4, 5. N over here is 1, over here is 2, over here is 3. And then the number of d's is like n minus 1. So at the end, n is like the total number. Over here it's 5. So over here it will be n minus 1d, whatever like the total terms are. So if I rearrange S, I can take this, put it here. A plus 2d, A plus d plus A. If I add these two, I get 2A plus n minus 1d. If I add these two, I get A, I get 2A. So A plus D plus A plus n minus 2d. So n minus 1d. So sorry, n minus 2d plus d. So n minus 2d from here, and then d from here. You add them up, you get n minus 1d. So this keeps repeating until we reach at the last one, which is again 2A plus n minus 1d. This happens n times. Uh, is this correct? And S is equal to, but I don't know if this is correct. Okay, let me open the other derivative website as well. Yeah, it's the first term plus the last term, half the times, right? Finding a term, sum of an arithmetic series. This is correct. So basically, we can find the sum. There are 26 in total. So n is 26, A is 1, and D is 2. N over 2, 2A plus n minus 1D. AD 26 is 1 and D is 2, 676 hot dogs in total. Hold on. 676 is the total hot dogs that were eaten. So the sum is 676. The last hot dog that was eaten is A plus n minus 1D. A n minus 1D. 51. Okay, that makes sense. After excavating for weeks, you finally arrive at a burial chamber. The room is empty except for two large chests. On each is carved a message, strangely in English. Exactly one of these chests contains a treasure, while the other is filled with deadly immortal scorpions. For either chest, if the chest message is true, then the chest contains the treasure. Okay. So we have a chest one, chest two. Oh, we can copy it here. Copy heading. We have this message and we have this message. Either chest, if the chest, if the chest message is true, then the chest contains treasure. Problem is you don't know whether the messages are true or false. What do you do? Uh, while the other is filled with a deadly immortal scorpion. The chest message. Okay. So chest one, chest two, you can have true, true, false, true, or false, false. For this first case, if it's true, true, did they say one of them is false? Did the messages are true? Okay, either one of them is true or false. But either chest, if the chest message is true, then the chest contains treasure. Either chest, if the chest message is true, but I don't understand if this chest is true, what does that mean? Okay, for this case, you want to know where the treasure is or the immortal scorpion. Where is the answer? I want to see the final answer. If this is true and this is true, Yeah, I don't know. Hold on a minute. Exactly one of these chests contains a treasure, while the other is filled with a deadly immortal scorpion. If chest 1 is true, that exactly one of these chests contains a treasure, while the other is filled with a deadly scorpion. If this statement is true, and if this statement is true, that for either chest, if the chest message is true, then the chest contains treasure. Then the treasure would be in this chest, right? Yeah, so if this message is true, and if this message is true, then either chest, if the chest message is true, then the chest contains treasure. But that's not, wait, if this message is true, for either chest, if the chest message is true, the chest contains treasure. They both can't be true at the same time, right? Because if this message is correct, then this chest should contain the treasure. But if this message is correct, then this will contain the treasure and this will contain a scorpion, which is a contradiction. So that can't happen. Wait, hold on. This case can't happen. They can't both be true. If this is true, then this is and this is false. Either just if the chest message is true, then the chest if this message is true, then this contains treasure. If this message is false, exactly one of these chests contains a treasure while the other is filled with a scorpion. Then that means both of them would be filled with a treasure, right? This is a contradiction. Both have treasures. If this message is false, either chest if the chest message is true, then it just contains treasure. And if this statement is true, that means if the message is false, then the chest, if the message is true, then the chest does not contain a treasure. Suppose this is true that one has treasure and the other has an immortal scorpion. Suppose this is false. If this is false, then if the chest message is true, then it just contains treasure. This being false means if the chest message is true, then the chest does not contain treasure. It means it contains an immortal scorpion. So then this would have the treasure, this would have the immortal scorpion, right? Open one contains treasure. What if they're both false? If this suppose this message is false, if the chest message is true, then the chest contains treasure. This being false means if the chest message is true, then the chest contains a scorpion. But the thing if the chest message is true, then it just contains a scorpion. That's a falsified version. But none of the message is true. So they both would contain a treasure, right? Exactly, one of these just contains a treasure while the other is filled with the deadly scorpion. But this message could be false. So both of them could have a treasure. Or both of them could have an immortal scorpion. Yeah, I think both of them would. Yeah, this would happen again. So this cannot happen. This will lead to a contradiction. One contains treasure, both have treasure, both have treasure. So I think you open just one. Maybe back in the days of your five small towns decided they wanted to build roads directly connecting each pair of towns. While the towns had plenty of money to build roads as long and as winding as they wished, it was very important that the roads not intersect with each other. Also, tunnels and bridges were not allowed for moral reasons. Is it possible for each town to build a road to each of the four other towns without creating any intersections? So, one, two, three, four, five. They want to build roads. So we have something like one road. We need second road. We need to connect these two. But that's possible. Like that. And what's not connected? This is not connected. So this one, two, three, four. This one, two, three. Because this is already connected. There's one, two. No, wait. This is already connected. One, two, three. And we have one, two. What about this last one? It's stuck. So this and this is the last connection we need, but it is stuck. My intuitive answer is no, there cannot be any intersection, but I need to revise graph theory. The four problems above illustrate the four main topics of this book: combinatorics, sequences, symbolic logic, and graph theory. However, there are other topics that are considered part of discrete mathematics, including computer science, abstract algebra, number theory, game theory, probability. Ultimately, the best way to learn what discrete math is to do it. Let's get started. Each section of the book will end with a small number of reading questions like the one below. These are designed to help you reflect on what you have read. In particular, the final reading question asks you to ask a question of your own. Thinking about what you don't know yet is a wonderful way to further your understanding of what you do. I should not have called this stream logics and proof. I should have called it discrete, like introduction to discrete mathematics. A double six domino set consists of tiles containing pairs of numbers each from 0 to 6. How many tiles are in a double six domino set? How many dominoes are in a double nine domino set? How many dominoes are in a double n domino set? A double six domino set consists of tiles containing pairs of numbers each from 0 to 6. So is it the same behind and front as well? So like let's say from the front it's 0 and 1, at the back it's also 0 and 1. Okay, I need to know more about this. How did you answer it properly? We are taking a problem solving approach to discrete mathematics. We will consider a large variety of questions that have a discrete feed to them. Consider how to answer those questions. This is not the only way to study discrete math. Another approach would be to study the tools used to solve the problems. If we were art students, we would study paintbrushes and easels and the composition of paint, which would be interesting for sure. But I think it is more enjoyable to actually paint those happy dated trees. That said, understanding your tools does help you use them. So in this section, we'll consider some basic tools used in discrete mathematics. We'll come back to these throughout our studies and understand them better as we need to. The tools in our subject are called discrete structures. They are mathematical objects that we use to represent parts of the problem we are solving. Structure is a good word since these things have fairly rigid constraints that make them what they are. Just like an apartment building is going to have different characteristics than an airplane hangar or a suspension bridge. The structure we will use the most in discrete math are sets, functions, sequences, relations, and graphs. We will now briefly preview each of these as we progress through our studies. Each will be explored in more detail. A set is an unordered collection of elements. This is fairly vague, but unless we want to spend a whole book trying to understand sets more precisely, it will be good enough for us. It is possible to define all mathematics using just sets. Even numbers can be thought of as sets themselves, but this is also not what we will do. Rather, we want to be able to talk about collection of numbers and other objects we want, and we will collect them in something we call a set. We can describe sets by saying exactly what elements are members of the set. We could specify this membership in words. Let A be a set of all natural numbers less than 10, or express it by listing all the elements. For example, A is equal to 3, 5, 7, or using something called set comprehension, also called set builder notation. An example is X is a set of natural numbers and X is less than 10. We will read that as A is a set of natural numbers that satisfy the property that they are less than 10. More precisely, the n symbol represents the natural numbers, which is itself a set. We define natural numbers to be whole numbers starting with zero. Not every book includes zero in this set. It largely depends on what area of mathematics you study. Since there are multiple ways, since there are multiple ways to describe the same set, we should be careful about what it means for set to be the same or different. A set is determined by its membership, so all four of the example describe the exact same set. 1, 2, 3, 4, 1, 2, 2, 3, 4. These are duplicates. Duplicates don't count. 2, 4, 1, 3 set are not ordered. And then x is natural number less than 5 and more than equal to 1. There are lots of things you can do with sets, which we will consider in more detail as we need to. We will see that it is often helpful to build new sets from ones we already have by taking union and intersection of sets, for example. Uh, is this entire section all of this, or are these separate? Oh no, this is all contained within. One way to define a function is as a rule that assigns exactly uh, each input exactly assigns each input exactly one output. The output is called the image of the input. Functions also come equipped with a domain, the set of all inputs, and a codomain, the set of all allowable outputs. You might also speak of range of a function, which is the set of all actual outputs, or put another way, the set of all images of elements from the domain. We write f from set x to set y to describe a function with name f, domain x, and codomain y. This does not tell us which function f is though. To define the function, we must describe the rule. I'm still confused with the difference between codomain and range. Is codomain like any superset of range? To define the function, we must describe the rule. Often this is done with the formula. For example, f of x is equal to x squared says that each element of the domain is mapped to its square. Or in words, like how we describe squaring function. The key thing that makes a rule a function is that there is exactly one output for one each input. Consider the function 1, 2, 3, 2, 4, 6 defined by 2x. If I wanted to plot graph of the function, we would draw the points 1, 2, 2, 4, 3, 6. Okay, we get the point. Of course, we are using mathematical objects here in ordered pair. This is not set since sets are unordered. How should we talk about ordered things? We will take this question up in the next section. I think they call it a tuple or a tuple. There's one more important consideration about how we define a function with a rule. A closed formula is one in which each output is given by an explicit rule based solely on its input. This is what most of us think of as a formula. For example, f of n is equal to 3n plus 1 is a closed formula since to find f of 5, we take input 5 and do something with it, multiply it by 3 and then add 1. What else could a formula possibly be? A recursive definition of a function tells us how to compute the output of a given input based on other outputs of a function. For example, we might insist that f of n is equal to 2 times f of n minus 1 if we also specify an initial condition that f of 0 is equal to 3. Then we can find f of 1 is equal to 2 times 3, which is 6. And then f of 2 is equal to 2 times 6, which is 12, and so on. What is f of 5 here? We have to keep doing this recursive thing until we find f of 5. Sometimes we are interested in not just a collection of number, but in what order those number appear. In such cases, we cannot use sets since they do not distinguish the order. Instead, we use sequences. We will consider both finite and infinite sequences. A finite sequence may be something as simple as 1, 2, 3. That is a sequence of 3 elements in that particular order. We might also call this an ordered triple, the same way that 7, 3 is an ordered triple. In general, we could use this, we could call this an n tuple if it has n elements. The key difference between sequence 1, 2, 3 and the set 1, 2, 3 is that we care about the order. That is, the sequence 1, 2, 3 is different from 2, 3, 1, while the set 1, 2, 3 is identical to 2, 3, 1. We will often use sequences as a counting tool. For example, a very simple counting question, how many wheels 100 cars have? Instead of answering just this one question, we generalize and ask how many wheels n cars have and get a sequence of answers. This yields the infinite sequence 4, 8, 12, and so on. The order of these multiples of 4 appear The order these multiples of 4 appear in is important since each number in the sequence corresponds to a specific version of the question. It's fine to think of a sequence of a number of a sequence of numbers as an ordered list. We can refer to terms simply as A0, A1, A2, and so on, and might refer to the entire sequence as an is more than or equal to 0. If you want to be a little more precise or and more abstract, we can think of a sequence as a function. Like the domain in the natural in is the domain is the natural number or some subset of consecutive natural numbers. Codomain is some set. You can think of the domain as the positions in the sequence and the image of those inputs as the term in the sequence. For example, we might consider the Fibonacci sequence, which starts with 1, 1, 2, 3, 5, 8. What is the fourth term in the sequence? So Fibonacci number, they like add the two previous term. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. I might say F4 is equal to 3. Note that there can only be one fourth term. There can only be one nth term for any particular value of n. So for any input, there is only one output. It would be perfectly reasonable to write f of 4 is equal to 3. And that really does look like a function. But we would like to use subscripts. We can also describe the terms in the sequence using a table. We might write something like the following. Yeah, 1, 2, 3, 4, 1, 3, 6, 10. This looks exactly how you would represent a function, even though this table describes a sequence of triangular numbers. Since sequences are functions, we can use any techniques to describe functions to describe functions to describe sequences. In particular, we might give a closed formula for a sequence by explicitly giving the function for nth term. For example, we have this. Alternatively, we can define a sequence recursively by saying how to get from one term to the next. This is explicitly used for the Fibonacci sequence. Okay, we'll study this and everything else sequence related in chapter 4. How are numbers 2 and 6 related? Why no 2 is less than 6? Also 6 is a multiple of 2. The two numbers are also even, but here's another fact. They are not equal. All four of these examples are relations, less than multiple of both even, not equal. And there are many more, infinite many relations for pairs of numbers. The examples above are all binary relations. in that they relate two elements. You could also consider relations between more than two elements. For example, we could consider the relation between Pythagorean triple on three numbers that holds precisely if they are sides of lengths of a right triangle. So the relation is true of the triple, but not of the triple 3 4 5, but not of 4 5 6. Since 3 square plus 4 square is 5 square, but not this. Notice we can talk about a pair or triple satisfying a relation. We might say that a pair belongs to a relation. A careful and formal way to define a relation is as a set of ordered pairs or triples. Consider the infinite set of all ordered pairs AB such that A is less than B. Every element in this set contains numbers for which the relation less than is true. And every pair of numbers for which the relation is true is a pair in the set. We can say that this set of pairs is the relation. Relations can have some standard properties, and deciding whether a particular relation has a given property can often help us understand the relation better. The less than relation is, for example, irreflexive because there are no elements that are less than themselves. It is also anti-symmetric since there are no distinct numbers A and B such that A is less than B and B is less than A. It is also transitive since if A is less than B and B is less than C, it must follow that A is less than C. These are few examples of relation properties though. Okay. Consider now we have graphs. Consider the set V. Which pair of numbers from that set add up to 7? We could have 1, 6, 2, 5, or 3, 4. 6, 2, 5, 3, 4. You can picture the set and the interesting unordered pairs as a picture called a graph. 1, 6, 2, 5, 3, 4. On the other hand, we might have to consider pairs of numbers whose sum is even. Then we will get the following picture. So 1, 5 even, 1, 3 even, 3, 5. Summing then gives even. We call these discrete structures graphs. Graph is a type of relation, one that is symmetric. If A is related to B, then B is related to A, and irreflexive. No element is related to itself. However, we mostly think of graphs as the drawing of dots and lines, and more precisely as the set of vertices together with the set of edges, where each edge is a two-element subset of the vertices. Notice that even here we are using the structure set to define the structure graph. Graphs show up in all sorts of real world applications in a class. Some students are friends with each other, so take the students to be vertices and edges to be friendships. So edges are the lines, right? And vertices are these dots. In geography, some countries share a border, so take the countries to be vertices and connect the pair of vertices with an edge if the countries share a border. So this will be chapter 2. Our list of structures could go on and on, but we'll stop here. We spend a little time looking at multisets, which are just like sets, except that they can have repeated elements. Since this is not a geometry class, we will not consider finite geometries or designs. Discrete structures are useful in computer science, but we'll stop short of studying linked list or red black trees. Although abstract algebra is a fascinating subject, we will not get to groups or rings or metroids or POS sets or Boolean algebras. These are examples of sets on which we define additional operations and study algebraic structures of how these sets and operations interact. Okay, logics and proofs. This is what the stream, like this was supposed to be the main part of the stream, but I think I will end the stream early and start this next stream. Logic is the study of consequences. Logic is the study of consequence. Given a few mathematical statements or facts, we would like to be able to draw some conclusions. For example, if I told you that if I told you that the particular real valued function was a was continuous on interval 0, 1, and f of 0 is -1 and f of 1 is 5, we can conclude that there is some point between 0, 1 where the graph crosses the x-axis. Yes, we can. Yes, we can, thanks to the intermediate value theorem for calculus. Can we conclude that there is exactly one point? Uh, no, whenever we find an answer in math, we really have a perhaps hidden argument. Mathematics is really about establishing general statements. This is done by an argument called a proof. You start with some we start with some given condition, the premises, and from these we find the consequence of interest, our conclusion. The problem is, as you no doubt know, arguing from a friend, not all arguments are good arguments. A bad argument is one in which the conclusion doesn't follow from the premises. Logic is the study of what makes an argument good or bad. In other words, logic aims to determine in which cases the conclusion is or is not a consequence of a set of premises. Okay, I wanted to, this is the main part I wanted to read. I think I will end this stream here. I will take a little break and then I will come back. So I'm planning to do logic and proof today only. I will just take a break and come back. Right then, I'll, um, I'll see you guys next. I will see you guys hopefully today. And yeah, I just end the stream here then. Okay, see you guys next time. Bye.